In this video, I'm going to work through a few of the examples from section 11 point notes along with you. If you haven't done so already, please go to the weekly assignments link in our class in Blackboard, open up the week 1 folder, and then print section 11.1 notes. Once you have done that, please go through the first several pages of your notes by following along the textbook. You can either read the actual textbook if you chose to purchase the textbook, or through this MyMathLab link. And again, please pick the second link here so that you'll have access to the ebook. You can open up your e-textbook. You can do this for every section of notes that we have. Here we are in MyMathLab. I'm going to choose the e-text link in order to open up our textbook. Click the e-text link again. Once it loads, we can choose section 11.1, and this looks just like the written physical textbook. So again, you can either read directly from the physical textbook or from the ebook. From the table of contents menu on the left side, I'm going to open up chapter 11 and choose section 11.1 limits. The notes that we have correspond exactly to the textbook. So if we compare our notes for section 11.1, notice example 1 is worked out on page 566 of either the ebook or the actual book. This ebook looks exactly like the textbook. So please read through section 11.1 in your textbook, work through the first several pages of the notes, and when you get to example 7, I will work a few of these problems with you. If you need to go ahead and pause the video and do that, please do so. If you are ready to begin, let's look at example 7. Now these are the types of examples that you could expect on your homework or also on an exam. So in example 7, we are trying to find the limit as x approaches 3 of the given rational function. The first thing you always want to try when you work a problem like this is simply to plug in your target value. If I plug the target value into the denominator, I notice I'm not going to get a 0 in the denominator, so I wouldn't have anything illegal occur. So this is the same thing as simply evaluating a function. We'll plug 3 in for all the x's that we see, and then we'll calculate. Notice as soon as I evaluate the limit, I drop that limit operator, this notation over here. When we calculate in the numerator, we have 9 minus 3, which is 6, and 6 minus 1 is 5. The radicand there is 4. So when we simplify, we have a limit of 5/2. In this case, the function value and the limit are the same thing. Now contrast this example with example 8. In example 8, our target value is 2. And notice if I plug 2 in for x in the denominator, I'm going to get a 0 in the denominator. So I won't be able to evaluate this one by direct substitution. Also, please forgive me, I've got a typo right here. To match the problem in the book, that sign should be a minus. So please correct that. Now, since we can't plug 2 in like we did on example 7, we're going to algebraically sidestep this problem. Our goal is to cancel that factor x minus 2 from the denominator because it's preventing me from evaluating the function. Now, do notice I'm not evaluating the function, so I'm going to go ahead and carry this limit operator to the next step. That's a pending operation that I haven't taken care of yet. Now, in the numerator, we have a factorable quadratic. We can factor this as x plus 3 times x minus 2, and in the denominator, we have x minus 2. Notice we now have a like factor in the numerator and the denominator that we can cancel. So this limit will be equivalent to the limit as x approaches 2 of x plus 3. Now, if I consider plugging my target value 2 in for x, there's nothing illegal that's going to occur. That is no 0 in the denominator, no negative under a radical, nothing like that. So I can go ahead and evaluate by direct substitution at this point. So if I plug 2 in for x, notice I'm dropping that limit notation, that limit operator on the left, because I'm actually evaluating the limit. So in this case, we come up with a limit of 5. Now, because I couldn't evaluate that by direct substitution, this simply means the limit is different from the function value. In fact, the function is undefined at 2 because we have a 0 in the denominator. But the limit exists. Remember, the limit describes the general behavior of the function, not necessarily the function value. Let's go on to example 9. Now, we always want to try to evaluate by direct substitution. Again, you can see in this problem that if I plug 4 in for x in the denominator, I'm going to get a 0 in the denominator. So we have to figure out some sort of algebraic trick that will allow me to evaluate by direct substitution. We can't factor like we did on the previous example, but we can do something called rationalization. You've probably learned to rationalize a denominator. Well, in this case, we're going to rationalize the numerator. That is, we're going to multiply the numerator and the denominator by the conjugate of the part of the fraction containing the radical. By conjugate, I mean we're looking at the same two terms, the square root of x and the 2, but we have a different sign in between. Okay, in this case, we will rationalize the numerator. Now, we're going to have a lot of FOIL to carry out in both the top and the bottom, so I'm going to add some parentheses here. And also observe, we have not yet calculated the limit. So until I actually plug that target value in, I'm going to carry that limit operator along. Now, our goal is eventually to get this factor, x minus 4, from the denominator to cancel. So in the numerator, let's go ahead and FOIL those two binomials. So if I multiply the first two terms together, square root of x times square root of x, that gives me x. Notice our outside terms are plus 2 square root of x. The inside terms are minus 2 square root of x, so those are going to cancel. We don't even have to write those down. And the product of my last two terms, negative 2 times negative 2 yes, that's correct. Negative 2 times positive 2 is negative 4. Now, I see that factor x minus 4. It matches the factor in the denominator, so I'm not going to factor out the denominator. I'm going to leave it as is. Now, the benefit of doing that is now we can cancel that common factor. I wouldn't have noticed that if I multiplied everything out. So the problem becomes equivalent to the limit as x approaches 4 of 1 over the square root of x plus 2. Observe, at this point, if I plug 4 in for x in the denominator, I do not get a 0 in the denominator. In fact, I'll calculate the limit. Again, when you plug in your target value, at that point you can drop your limit operator because you're carrying out that operation. We're plugging 4 in for x. We have 1 over 2 plus 2, so our limit there is 1/4. Okay, so at this point we've looked at a couple of tricks. First of all, we've attempted direct substitution. If you can evaluate the limit by plugging in your target value and you get a real number, then you've calculated the limit. If that doesn't work, you can try to factor and cancel, or in this case, we looked at rationalizing the numerator. You can rationalize either the numerator or the denominator. Let's look at the next one, example number 10. Find the limit as x approaches 1 of the given rational function there. Again, I'm unable to plug in the target value directly because that would give me a 0 in the denominator. So, as we did on a previous example, let's see if we can factor and cancel. We're not calculating the limit, so I'm going to carry my limit operator. The numerator factors as x minus 1 times x minus 1. We could write that in shorthand notation as x minus 1 squared, and we have an x minus 1 cubed in the denominator. Now, we can cancel 2 of those factors, but this leaves an x minus 1 in the denominator. Now, in this case, I'm unable to go ahead and plug in my target value, 1. So we can evaluate this limit by reasoning, or to help our reasoning, we could consider a graph. Feel free to graph this on your graphing calculator. I'll just make a quick sketch of this graph over here to the right. This is a rational function. It happens to have a vertical asymptote at 1. That is where that denominator is equal to 0. So I'll sketch this in as a boundary line. And this is a pretty rough sketch, but we'll get the idea. This rational function also has a horizontal asymptote on the x-axis. That is, it's just going to settle down over the x-axis. Again, please feel free to graph this with your calculator. If we graphed the function, we would obtain something like this. Again, it's a rough sketch. We want to figure out what happens to the function value as the x values get closer and closer to 1. This is from the left and from the right. So if I think about as my x values get closer and closer to 1 from the right, what are the y values doing? Well, the y values are heading up towards infinity. So as x approaches 1 from the right side, the y values, or the function value, is approaching infinity. Let's see what happens to the left. As I approach x equals 1 from the left, so x is approaching 1 from the left, what's going on with the y values? Well, as we move in towards 1 from the left, the y values are heading towards negative infinity. So as x approaches 1 from the left, the function values are getting closer, or at least decreasing without bounds. Since the function approaches two different directions on either side of our target value, we say the limit does not exist. So that's one of those tricky ones. Be prepared to sort of reason through that. Inspecting a graph can be tremendously helpful. Now, you may want to pause the video and read through the text about limits at infinity. And the next examples that I want to work with you begin with example 12. When you get ready to work those, unpause the video and we'll work through these together. If you're ready to work these, notice the target value in these examples is infinity. Anytime we want to calculate a limit at infinity, we're going to divide all terms in both the numerator and the denominator by the highest power of x in the denominator. So in this case, it's going to look pretty bad, but it's going to simplify it a bit. Divide everything by the highest power of x in the denominator. So I'm going to divide each term in the numerator by x, each term in the denominator by x. And then I'm going to simplify. So we have the limit as x approaches infinity of 8 plus 6 over x divided by 3 minus 1 over x. Now, as you read from the text, as x approaches infinity, 6 over x approaches 0. That is, as the denominator gets large, without bounds, that fraction gets smaller and smaller. The same thing happens to the 1 over x in the denominator. As x approaches infinity, that fraction gets smaller and smaller and smaller. You can see now we have the limit of a constant. The limit as x approaches any number of 8/3 is 8/3. So in this case, we get a limit of 8/3. Do notice in the original function, the degree of the numerator was 1. That is the highest exponent I can find. The degree of the denominator is also 1. And you're going to see a rule of thumb, a quick, easy way to evaluate this limit. If your numerator and denominator have equal degrees, your limit is the result of the ratio of leading coefficients. Okay? So let's look at example B. We're going to apply the same procedure. We're going to divide every term in both the numerator and the denominator by the highest power of x in the denominator. In this case, it's x cubed. So if we divide 3x by x cubed, 2 by x cubed, it looks like we're making it worse, but this will help us with our analysis. And then we'll simplify as much as we can. Again, carry that limit operator until you actually find the value. 3x over x cubed is 3 over x squared. Can't do anything here with this second term. We get a 4 in the denominator minus 1 over x cubed. Notice all those fractions. They've got a variable in the denominator. X is approaching infinity. So in each case of those fractions, as the denominator increases without bounds, the fraction crashes down to 0. So this looks like the limit of 0 over 4, which gives us a limit of 0. Okay? To understand kind of a shortcut for working this one, anytime the numerator has a degree that's less than the denominator, your limit will always be 0. Okay, next example. We're looking at the limit as x approaches infinity of another rational function. We're going to divide everything by the highest power of x in the denominator. So we have the limit as x approaches infinity of 3x squared over x plus 2 over x, and the denominator 4x over x and minus 3 over x. As we did above, we can go ahead and simplify each fraction. We end up with 3x plus 2 over x over 4 minus 3 over x. Considering those fractions, as x approaches infinity, the fraction crashes down to 0. So those two terms head to 0, and we're left with the limit as x approaches infinity of 3x over 4. Well, if x is approaching infinity, then this numerator 3 times x is also approaching infinity. And we have a number increasing without bounds in the numerator divided by 4. Therefore, we say the limit is infinity. Technically, the limit does not exist, but we can say that we can describe the general behavior of the function saying as x gets larger and larger in the positive direction, the function value does the same. Y's increase without bounds. So the limit does not exist technically, but we can call it infinity. It's kind of an oxymoron to say that something has an infinite limit. Okay? One more problem here, and back to this one. Do notice in this case the degree of the numerator was greater than the degree of the denominator. In that case, the limit will either be positive infinity or negative infinity. So we've looked at 3 cases here. The degree of the top is equal to, if the degree of the top is equal to the degree of the bottom, the limit is the ratio of leading coefficients. If the degree of the top is less than the bottom, your limit will always turn out to be 0. And if the degree of the top is bigger than the bottom, the limit will either be positive infinity or negative infinity. You can memorize those 3 rules, or you can work it out like we've been doing. It works the same way every time. Divide by the highest power of x in the denominator. Last example for this section. Let's follow the procedure to divide by the highest power of x in the denominator, which is x squared. Do notice this is the case where the degree of the numerator is greater than the degree of the denominator. So we can anticipate the limit to be either positive infinity or negative infinity. We'll check out our signs here. And reduce. So we end up with 5 minus 4x over 3 plus 2 over x minus 1. Got one fraction that's going to 0 as x approaches infinity. And notice in the numerator, as x approaches infinity, negative 4x approaches negative infinity. And I have a positive 2 in the denominator. So we have 5 minus a really big number, that's going to be a really big negative number, divided by 2. Therefore, our limit is negative infinity. Again, technically, the limit does not exist. I'm going to abbreviate D and E for does not exist. But we could say the general behavior of the graph is that as x gets larger and larger without bounds, the y values head towards negative infinity. You can finish out the rest of the notes by reading the textbook. Once you have completed your notes, then you can proceed to complete your MyMathLab homework. Again, to complete your MyMathLab homework, just follow this link in our course in Blackboard. Click MyMathLab. Choose the second link. That's usually most useful because you have access to more options that way. Then When your page opens up, choose Assignments, and you can get started on section 11.1.